Hey, welcome back to our second class in Engineering 250, Digital Logic Design. Several things to talk about today. Again, largely a refresh of topics from CSE 120, but also going a little bit beyond. We're going to talk about logic gates, identities, truth tables. I also want to dig into a data sheet for a typical logic gate and show you where to find information on these physical devices that we work with sometimes. I want to review conversion between hex, octal, binary, and decimal, and also talk about doing non-integers in binary. So how do we convert something like 2.5 from decimal to binary? Look at ASCII codes, and then talk a little bit about A to D converters, and that'll do it for this class. So let's begin with the idea of logic operations. So in a math course or in CSE 120, we deal with real numbers. So we could have a voltage of 2.61 volts and a current of 15.7 milliamps. In digital logic, we basically deal with two numbers, a 0 and a 1, and that's it. Everything is built up out of just these two building blocks. So instead of having 10 digits, 0 through 9, we have two digits, a 0 and a 1. And these binary digits, these are called bits, right? Bit for binary digit. And in some sense, this simplifies our life because we don't have as many things to deal with. So whereas we need a multiplication table in grade school to teach us how to multiply numbers, from 0 to 9 or 0 to 20, multiplication in some sense of binary numbers is simple because you've only got a few things you can multiply, zeros and ones. um, so the kinds of things we do with these binary digits are different from the things we do with, say, numbers when we learn multiplication, division, things like that. These binary operations, these are logical operations. So logic operations, and this is stuff that was studied, almost 200 years ago in the 1800s. George Boole and people around that time were studying questions of how people think, how do we reason, how do we come to conclusions, and a lot of that was based on the idea of true or false, yes or no. And so some of these early studies were trying to understand, if I know that this and this is true, what else do I know? So this is a very old discipline, and it's uses the term logic in a lot of places, even if we're using these bits to do calculations on numbers or display information on a website. At some level, it's all logical operations going on underneath. So what are the kinds of logic operations we can do on a bit? Well, we have a simple operation called NOT. And if we take the NOT of a 0, we get 1, and the NOT of a 1 gives us a 0. And we can think of this, if 0 is false and 1 is true. If something's not false, it's true. If something is not true, it's false. We can also think of an OR, which takes two things. And if we have a pair of zeros, the OR of those is 0. But if we have at least one 1, the OR will be a 1. And so again, we can think of, if this thing is false but that thing is true, and then we ask, is this true or is that true? The answer is yes, that's true. But if both of these things are false, are we on the planet Neptune, or are there 10 days in the week, right? Both of those are false, and so the or of that statement is false. And so we can define some basic operations, but trying to define them in this way gets cumbersome, right? So we use what's called a truth table, and I know you've seen these in CSE 120, but again, we're doing a bit of review and then building on top of what we may have seen before. So let's make a truth table for an OR gate. So we typically have a pair of inputs. And then we can say A or B. And so there's only 4 possibilities. For A and B, they can both be false, B can be true, A alone can be true, or they can both be true. And so for each of these, we can list what we get when we take the OR operation. And if at least one of these is true, then the OR is true. And we have notation that we use for representing an OR. We can use a plus sign. We can also represent an AND gate, and we write that with a dot, or sometimes just A and B next to each other, so it looks like multiplication. And an AND is true only when both of the inputs are true, so an AND looks like that. We can also complement these, or take the opposite of them, so we can have what's called a NOR, and we write that as A or B with a bar on top. And this just means do an OR, but flip zeros to ones, ones to zeros. So instead of this 0, 1, 1, 1, we get a 1, 0, 0, 0. And we have an AND. And that we write as an AND with a bar on top. And it's the opposite of the AND column. So 1, 1, 1, 0. And we have an exclusive OR, which we write like an OR, but with a circle around the plus sign. And an exclusive OR looks just like an OR, except only one of these inputs can be 1. So this last row will be a 0. And then we can have an exclusive NOR, which we write as an exclusive OR with a bar, and that just complements the XOR. And so there's 6 of our basic logic operations for 2 variables. And an interesting interpretation of an XOR is we can think of this as a difference function. Are A and B different from each other? Here A and B are different, so the XOR is 1. Here A and B are different, so the XOR is 1. But when A and B are the same as each other, the XOR gives us a 0. And we can think of an XNOR as a same function. Tell us if A and B are the same. Well, here and here they're the same, and in those places the exclusive NOR is a 1. Alright, and we can also make a truth table for our simplest operation, which is just the negation of a variable. So these variables, are placeholders for binary numbers. So if we have a binary number, we can call it A. It's either a 0 or a 1, and its negation or not, or inverse or complement, is either a 1 or a 0. It's the opposite of what A is. Now, when we build circuits out of physical devices that perform these operations on inputs. And so we have symbols that we use for these. This is what an OR gate looks like. This is an AND gate. And when I draw these, I like to put a little symbol inside to make clear what kind of gate it is. Normally this curved back makes this an OR gate, but that can be a little tricky to see clearly sometimes. So I put a plus sign inside an OR and a dot inside an AND. And then, and here's the output over here. And then if we want a NOR, well, we make an OR gate, but we put a little bubble or circle on the end, and that circle means negate the output. Same thing for an AND, draw an AND gate, but put a little bubble on the output. And then exclusive ORs, we put a little extra thing on the input here. And again, I'll actually put the XOR symbol inside. So that's an exclusive OR gate. And then exclusive NOR looks the same, except we put a bubble on the output. So that's an exclusive NOR. And then NOT, we just draw a triangle with a bubble. And we'll deal with this as it comes up, but I'll give you a heads up. Sometimes we see these bubbles other places. these little circles, we call them bubbles, generally mean not. They generally mean an inverter. And so you may see something like this. So we have A and B, and we have some output X. So what does this gate do? Well, we think of that A as going through an inverter, and we think of B as going through an inverter. And then we AND the two of those, and X is equal to that. So a picture like this, we can think of it logically as doing the same thing as this. But for certain reasons, it's fairly common to want to put inverters different places here and there. And so we just draw the circle part of the NOT gate, and that gives us an abbreviated way to draw more complex functions like this. So that's the deal with truth tables, right? We can always write a truth table to explain how something behaves, and we'll see this a lot for more complex operations. And whereas, a simple OR gate or NOT gate, we can write something like this, that gets really cumbersome. So we're always going to use truth tables. And we're going to try to get used to writing our inputs in this particular order. The reason being, eventually, next class we'll talk about converting between these binary patterns and numbers. Actually, we'll do that today. And so if we do that conversion, this will turn out to be the number 0, 1, 2, 3. These are written in a very natural order. And so we'll want to get in the habit of making sure we list things in that order in most cases. All right, well, once we have these logical operations, we can start talking about properties. And there's a number of properties or identities that apply to logic operations, and we've seen these in 120 also. So for example, A ANDed with B is the same as B ANDed with A, and A ORed with B is the same as B ORed with A. Right, so these operations are what we call commutative. We can also have things like an AND gate with 3 inputs. We can take A ANDed with B ANDed with C, and to evaluate that, we can do things in order. We can take A, B, and AND that together, and then take the result of that and AND it with C. Or we can take B and C, AND those together, and then AND the result with A, and we'll get exactly the same thing. So this is called commutivity. This is called associativity. And these concepts will come up again and again. They come up in different courses. They come up when we deal with things like set theory in CSE 215. They come up when we deal with programming languages. All of these operations have this property of commutivity, this property of associativity. We also have things like distribution. If we take A and we AND it with B or C, we get the same thing as A ANDed with B, ORed with A ANDed with C. So sometimes I'll put a dot in here, sometimes I won't. If you see two variables next to each other, it's an AND operation. So just like multiplication, we don't always put a multiply symbol. So this distribution, this works like, regular integers in plain old algebra. We can take A times B plus A times C. This will be the same thing as that. And if we want to confirm that any of these are true, we can do that with a truth table. So we'll come back with we'll come back and check this one in a minute, but let's look at a few more identities. If we take a variable A and we AND it with 1, we just get A. In other words, if we take the AND of A with something that's always true, we just get A. If we take A and we AND it with something that's false, we get a 0. If we take A and we OR it with 1, we get a 1. If we take A and we OR it with 0, we get A. If we take A and we OR it with itself, we get A, which is the same as if we take A and we AND it with itself. And so you can find these identities in your textbook, and there's a whole page of them, and they're useful to be familiar with. We won't actually use them too much where we think of them as identities, but we'll do these kinds of equivalences all the time when we're designing circuits. We'll often say, okay, I want to just take these two things and OR them, but the second one happens to be on top in our circuit, and so we'll put that into our OR gate first. We won't even think about it. So look at the identities in your book, so that you've at least seen them. And we'll encounter these when we're simplifying equations and things like that. All right, so at this point, let's take a look at what these symbols correspond to, these logic operations. Let's look at the physical devices corresponding to them. So if you go to the website engrcs.com, that's the department's website, you'll use this a fair amount. You can find scheduling for office hours or advising on here. If you just go to engrcs.com, it may ask you for a password. If it does, the password is just Clark, lowercase. That's just to keep out bots. But it will bring up a page like this. And over here on the side, component specifications, this will take us to a link where we can see what are called data sheets for different logical devices. So let's look at a 2-input AND gate. So I can click on this, and this brings up a data sheet for what's called a 7408. And there's letters that come before this, there's letters that come in the middle, but the main thing that makes this an AND gate is the 74 and the 08. And this is an extension of what used to be called the TTL line of devices. Texas Instruments made these in the 70s, and they were all 74s followed by a 2 or 3 digit code identifying their behavior. So this LS specifies that this is a different kind of logic inside, something called low power Schottky technology instead of TTL, transistor logic. We can mostly ignore that. Just look for the 74 and then a 2 or 3 digit code. 7408 means an AND gate. And here's a picture of the physical device. It's got 14 pins coming around the side. And if you look at one of these devices, it's a little package. Looks like that. It's usually got a little notch on one side to tell you which end is which. And then there's these pins coming out of the side, and these pins come out and go down at an angle, and you can put them into protoboards or breadboards, which we'll see when we play with Tinkercad some more. So here's a picture. Pictures are always from the top of what this device looks like. And you can see that it's got a pin labeled ground and one labeled VCC. VCC is power. Ground is ground, 0 volts. So to make this chip work, it needs power. It needs to be plugged in. We plug this pin to ground, 0 volts, and we plug this pin 14 to 5 volts. And we need to know VCC means power, which means 5 volts. And we'll see that in the data sheet in a minute. And this thing has 4 of these AND gates inside. And so this gate, for example, takes inputs from pin 1 and pin 2, and those are labeled A1, B1, and it makes an output on pin 3, which it calls Y1. And here's a truth table showing how Y relates to A and B. Now, this table uses L and H for low and high, 0 and 1. You'll see both, but L and H are pretty common. So if both inputs are high, 1, then the output's high. If either or both inputs are low, the output is low. And there's a little key. H is high logic, L is low logic level. So that's all you need to know really about this chip once you've used a few of these chips. But if you need more information, you can find, for example, what's the supply voltage, VCC? Well, it should be 5 volts. It could be as low as 4.75, as high as 5.25, but it's got to be pretty close to 5. And there's an entirely different set of devices that begin with a 54 instead of a 74. These are what are called mil-spec devices, right up here. And mil-spec devices will tolerate a wider range of supply voltages, a wider temperature range. These will work up to 125 degrees Celsius, whereas our 74 chips only work up to 70. Um, and so you can find more information in here. You can find how fast this device works. If I change an input to an AND gate, it doesn't change the output immediately. It takes a bit of time. It could take as much as 18 billionths of a second, 18 nanoseconds. And you can find physical information about the device. So this is what the chips that we would use in the lab typically look like. There's the top view. There's the 14 pins, pin 7 down here, 14 up here. There's that little notch to tell you which end is which. Here's what it looks like directly from the side. Here's what it looks like from the back. And you can see those little legs coming down that will go into the holes of a protoboard. And, you know, it tells you how far apart those are, what angle these legs come out at, 10 degrees max, and so on and so forth. So a lot of information in this data sheet, most of which we don't worry about. But, you know, if you were building a device and you needed to use this type of chip with these leads that come directly out the side, you'd need to know how far apart are they, how long are they, and so on and so forth. And usually this information is given to a machine that automatically builds your circuit boards for you. So that's a typical data sheet. Again, most of the information we need is usually near the beginning, and it's mostly knowing what the pins are. So this is called the pin out, and knowing what the truth table looks like. All right, so the next thing to talk about is this notion of numbers, because a lot of what we do with these circuits is we deal with numbers. Now, in school, we learn how to write numbers like this. And even if you've never seen this number before, most of us know what this number is. And we understand what its value is. We understand how we could multiply it by 3, for example. We understand that if we write another number, this may be bigger or smaller than it. And, you know, we have no direct experience with this particular number, but we completely understand this number. And the reason for this is that this is not just a random set of symbols. There's a specific way that this set of symbols is associated with a number. And this is what we call weighted positional notation. Fancy words. But all it means is that each of these digits corresponds to a power of 10. 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and so on. And the digit is a multiplier. So this says, let's take 6 times 10 to the 0, which is just 6. Remember, 10 to the 0 is 1. This is 7 times 10 to the first, which is 70. This is 7 times 10 squared, which is 700. This is 1 times 10 cubed, which is 1,000. This is 2 times 10 to the fourth, which is 20,000. This is 3 times 10 to the fifth, which is 300,000. And this is 4 times 10 to the sixth, which is 4 million. And then we add these. And what do we get? We get 4,321,776. It's so ingrained in us that it seems silly to write it out like this. Because, you know, of course, this number means this number, right? That's the set of symbols we write for that number. But the reason it's that value is because each of these gets multiplied by a power of 10. Well, the reason to go into that right now is because we can also do this in binary. We can write a binary number like this. And again, this means 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So this number means 1 times 2 to the 0, 0 times 2 to the first, 1 times 2 squared, 0 times 2 cubed, 0 times 2 to the fourth, and 1 times 2 to the fifth. So 1 times 2 to the 0 is 1, 0 times anything is 0, 1 times 2 squared is 4, 0 times anything is 0, and 1 times 2 to the fifth is 32. So if we add these numbers together, 32 plus 4 plus 1, that's 37 decimal. And I'll put a little period here to say that this is decimal, or what we call base 10. So this is our binary notation for the number 37. And sometimes we'll write binary with a little 2 down here to say this is base 2. But since most of what we work with is binary, if we don't write something down here, it probably means a binary number. But you know, there is potential ambiguity. If I write this, that could be the binary number for 3, or it could mean the decimal number 11. So if it's unclear, we need to either know from context, or you need to be told this is a binary number or this is a decimal number. So usually it should be clear from context, but you know, on tests or something, just always ask if it's not clear. So so converting from binary to decimal, not a bad problem, right? Converting from decimal to binary can be a little trickier. So suppose I want to go from decimal to binary. For example, let's write the number 53 in binary. So we can try to, you know, find powers of 2 that add up to 53, but there's an algorithm we can use for this, and this will always work. Begin with 53 divided by 2, and what do we get? We get 26 with a remainder of 1. Take 26 divided by 2, we get 13 with a remainder of 0. Take 13 divided by 2, we get 6 with a remainder of 1. 6 divided by 2, we get 3 with a remainder of 0. 3 divided by 2, we get 1 with a remainder of 1. 1 divided by 2 gives us 0 with a remainder of 1. And 0 divided by 2 gives us 0 with a remainder of 0. So we're just taking our original number, dividing by 2, and writing down, you know, the whole amount that we get with a little bit left over. So 26 with a remainder of 1. And then we take that 26 divided by 2. We get 13 with a remainder of 0. And we're only interested in these whole parts. That's what we divide the next time. But when we're done, it's these remainders that will give us our final answer. So if we write these down as a number, that will be our number in binary. And you know, if we continue doing this, we could continue getting zeros on the left. Zeros on the left don't change anything. So our binary number is 110101 base 2. And this should be equal to 53 in decimal. And we can double check this, right? If we know our powers of 2, this will be 1 plus 4, 8, 16, 32. So that's 48, that's 52, that's 53. So this is correct. So we can go back and forth between binary and decimal pretty easily. But it's even easier to go between binary and other representations. So one representation we'll use is octal. So here's a 12-bit number in binary, and if, you know, this was our credit card number, we were giving it to someone on the phone, it would be really confusing because humans don't deal well with lots of things that look the same. So one thing we can do is we can break our number into groups of 3, and write a symbol for each group of 3. And what we do is we basically take this 3-bit number and convert it to decimal. So 101, that's a 1 plus a 4 is 5. A 1 plus 0 plus 0, this is a 1. This is just 2 to the second is 4. And this is another 101 is 5. So we could say that this number equals 5415, base 8, or octal. And we always want to start this conversion from the right, because remember, we can always add extra zeros to the left without changing the value. So if we wanted to convert the number 1111 into octal, well, we would break this into a group of 3. We could imagine there's extra zeros on the left and break that into a group of 3. So 111 is 7, 001 is 1. This is 17 in octal. And it's a lot easier to type in a number like 5415 than 101100001101. So it's a convenience. And if we want to go in the other direction, it's actually a little bit easier. If someone gives us a number like, 234 octal, and we want to write that in binary, just write 3 bits for each digit. So the number 2 looks like this, the number 3 looks like this, the number 4 looks like that. So in my head, I thought of this as groups of 3, starting from the left. And the number 2, well, there's actually, an extra 0 there. Let me do that again. Number 2, number 3, number 4. So let's write this as a 3-digit number. Let's not skip too many steps. So this is the pattern corresponding to a 2. This corresponds to a 3. This corresponds to a 4. And then, we can go ahead and drop that leading 0 and just write this as 10011100 in binary. So that's how we convert between octal and binary. And then sometimes it's more convenient to break things into groups of 4, which is what we call hexadecimal. And same idea. So break your number into groups of 4, starting from the right. And if you don't have, a multiple of 4, add extra zeros to the left. So 1001, that's 1 plus 8 is 9. 0111, that's a 7. 0101 is a 5. 1000 is an 8. 1110, that's 8 plus 4 plus 2. That's a 14. But if I write a 14 down here, I've got some confusion. This looks like 975,814. But that's not exactly right. What I really want is a symbol that means 14. So I know this is 97,580 something, right? In hex. Because if I write down a 1-4, I don't know if that's one symbol for this, or if my number ended with this, a 4 followed by a 1. So we need a single symbol to represent the number 14. And so we use the following table. If we want to represent the number 1010, 10, we use an A. 1011, 1100, 1101, 1110, and 1111. So this pattern 1110, we would write that as an E. So we would say this binary number is equal to 9758E in hex. And sometimes we write a hex, sometimes we write a 16. In programming languages, we put a 0x in front of our number. 0x9758E means this is hexadecimal. Sometimes you see the letter H before or after this to mean hexadecimal. So there's different notations. But each of these represents 4 digits in binary, a 4-bit binary number. And if someone gives us this number and we want to convert it to binary, just write down the 4 bits corresponding to each digit. So there's a 9, there's a 7, there's a 5, there's an 8, and there's the pattern corresponding to E. And so just by looking at this, I was able to reproduce this 20-bit number faithfully without a whole lot of effort. And if you want to go between hexadecimal and octal, for example, it's easiest to go to binary first. Because, you know, this is grouped in sets of 4, octal's grouped in sets of 3. So binary is a good intermediate step. All right, well, we can represent numbers a variety of ways then in binary, but we can also represent things different from numbers. And one thing we can choose to represent is letters. And so we have what's called an ASCII code. And ASCII is basically an 8-bit code, and different patterns of 8 bits correspond to different symbols. For example, the 8-bit pattern in hex 41, in octal 1001, corresponds to the letter A. So what does 41 hex look like? Well, here's a 4, and here's a 1. So that's 41 hex. Again, in octal, this would be a 1, 0, 1. And this corresponds to the letter A. Why? Because somebody decided almost 100 years ago that that's what would correspond to the letter A. And 42 hex, 66 decimal, corresponds to the letter B. And so the alphabet, you know, begins at decimal 65, goes up through 97, goes up through 90, and then we have some symbols, and then at 97 we begin the lowercase alphabet, which goes from 97 up through 122, and we have symbols for digits and for punctuation, and we also have ASCII symbols for what are called control characters. So some of these are meaningful to us. For example, a line feed or a new line is a way to move from one line of a file to the next. A carriage return, this is what older operating systems use to indicate the end of a line. A tab moves over a fixed amount of space. A bell used to actually ring, a mechanical bell on old teletypewriters. If you were looking at the contents of a file and you hit a character with ASCII code 7, a little mechanical arm would hit a bell and it would make a ringing tone. And so these we don't usually worry about too much. Mostly we're going to deal with these printable characters, starting with a space and going up through a tilde. So, you know, this table is in your textbook. But more generally, we can use sequences of bits to represent lots of different things. For example, if I had a set of 16 things I wanted to label, I can label those with 4 bits. And I could just make an arbitrary decision. I could say, okay, bit pattern 0000, that means my pen, and 0001, that means my eyeglasses. And, you know, we could assign a mapping between patterns of bits and whatever things we're trying to label. And there's a good little formula to know that if you have a certain number of bits, the number of things you can identify with that many bits is at most 2 to that number of bits. So ASCII is an 8-bit code. It's actually 7 bits. But with 8 bits, we can identify 256 different things. ASCII, we only really use 7 bits, so we can identify 128 different things, and there's all 128 of them in this table. EBCDIC, an older code that was used by IBM, was 8 bits and had 256 things you could identify. One of the downsides of EBCDIC was your letters were not sequential. There were gaps in between the sequence of 26 uppercase letters. So ASCII eventually became the standard. All right, last thing we want to talk about today is analog to digital conversion. And again, back in 120, we're used to dealing with things like a voltage, which is exactly 2.223 volts, or a current, which was 11.42 milliamps, or a resistance, which was 123 ohms. And in binary, we deal with ones and zeros, but we can put those ones and zeros together to make bigger numbers. And we'll see how to make fractional numbers like this in a minute. But we sometimes need to go between this analog world and this digital world, where we have everything represented perhaps with ones and zeros. But more than just using ones and zeros, there's this notion that when we set the voltage on a power supply, we can change that voltage continuously. We can go from 2.223 to 2.224, or even something in between those. It's a very smooth kind of continuous change. Whereas in binary, we have 0, 1, 2, 3, 4. We have these jumps. These are in some sense more like integers. These are more like real numbers. But we can still approximate these ranges of real numbers using digital numbers. And so we can think of A to D conversion. This is analog to digital. And here's the basic idea. We'll get into this more in Engineering 270. But the basic idea is, suppose you have a waveform, and let's say it's changing between 0 volts and 5 volts, and it's going up like this. So if you were to write down in your lab book what the voltage was at different points in time, you would say, it's 0.7 volts, and here it's 1.2, and here it was 2.1, and here it was, 2.63, and so on. But we could approximate this with a binary representation. And a simple way to do this would be to split this in half and say, hey, anything below this line, we're going to write that as a 0. And anything above, we're going to write that as a 1. And so we have a very crude representation of this waveform, where we pretend, okay, your waveform up to here looked like a 0, and then at this point, it looked like a 1. Now, that square line is obviously not the same as that smooth curved line, but it kind of gets the idea of it, right? It's an approximation. But we could do a better approximation by breaking our input into 4 bins and saying, okay, everything between here and here, we're going to represent in binary as a 0, 0. Everything from here to here will be a 0, 1. Everything from here to here will be a 1, 0. And everything from here to here will be a 1, 1. And so all of this part of our signal would look like a 0, 0. And then everything from here to here would look like a 0, 1. And then everything from here to here would look like a 1, 0. And then everything from here to here would look like a 1, 1. And so we get this stair-step function that kind of follows the shape of this curve, but is obviously, far from exact. But it's a better approximation than our original single step function. And so we can think of this as a 2-bit A to D, whereas this original step function was a 1-bit A to D. And the more bits we use, the better we can track this original signal. But we can never get it exact. We're always approximating. So We can talk about, for example, an 8-bit A to D, which means we're going to use 8 bits to represent any of our voltages, in this case between 0 and 5. Well, this is going to give us a pretty exact representation of our waveform. Not perfect, but if we break this into 256 bins, we might not be able to tell the difference between this voltage and that voltage. But, does that really matter? Well, it depends. But it's going to be a whole lot better representation than this 2-bit or this 1-bit representation was. So let's just look at a few numbers for that. And, all of this is spelled out in the textbook, and we'll do some problems with all these concepts in class. But suppose we have an 8-bit A to D. And suppose we know that our input goes from 0 volts to 5 volts. Well, 8 bits means we have 2 to the 8th, or 256 different numbers. So we can basically split this 5 volts into 256 small regions or buckets. And so if we have 5 volts and we're splitting it into 256 regions, each of these, right, from one representation to the next, is 5 over 256 volts, or approximately 10 millivolts, 20 millivolts, right, 1/50th. So that's a pretty small voltage range, but anything between 0 and 20 millivolts, we can't tell the difference. We're just going to write that as a 0. So 0 to 20 millivolts, and 20 to 40 millivolts, we might just write that as a 001 and a 010. Let me put some other bits in the front. This might represent 40 to 60 millivolts. So we can say, 45 millivolts looks different from 50 millivolts, but 45 looks the same as 35, looks the same as 20, looks the same as 39. So this would be what we call our resolution. It's how closely we can tell the difference between two voltages. And the more bits we have in our A to D, the better our resolution. And so we can have a 10-bit or a 12-bit or a 14-bit A to D and get very precise resolution. Or we can have, a 1-bit A to D where our resolution is 2.5 volts. Everything from 0 to 2.5 volts, we represent it with a 0. 2.5 to 5, we represent it with a 1. So the resolution depends on the number of bits and also on this range. There's one other variable in here, which we can think of as an offset or a bias. And that has to do with where our signal begins and ends. And so, for example, I might have a signal which goes from minus 2.5 to positive 2.5 volts. And maybe it's, doing something inside there. And so I would have a different range of values. Again, if it's an 8-bit, maybe maybe this would correspond to negative 2.500 to negative 2. And I gotta do my calculations on the fly here. But if this is 20 millivolts, negative 2.480 volts. And this would be negative 2.48 to negative 2.46, and so on. And so we still have 256 bins here, but we just kind of shifted them down in this case from what we were using up here, where we went from 0 to 5, we shift down, we go from minus 2.5 to 2.5. So we'll look at that in some practice problems, and like I say, we'll dig deeper into that in Engineering 270, the microprocessors class. All right, let's take a look at converting between non-integers and binary. So suppose we have a number like 101.011, and we want to convert that to decimal. Well, the numbers to the left of the decimal point, we already know how to do those. Each of those bits corresponds to a power of 2. So 2 to the 0 is the 1's place. 2 to the 1 is the 2's place, and that's multiplied by 0. And 2 to the 2 is the 4's place. So 4 plus 0 plus 1, that's a 5. So the left of the decimal point is going to be a 5. But we have to figure out what this means, 0.011. Well, it's exactly the same thing. This is the 2 to the negative first place, 2 to the negative 2, 2 to the negative 3. So 2 to the negative 1 is 1/2, which is 0.5. 2 to the negative 2 is 1/4, which is 0.25. And 2 to the negative 3 is 1/8, which is 0.125. And so 0.011 means 0 times 0.5 plus 1 times 0.25 plus 1 times 0.125. And 0.25 plus 0.125 is 0.375. And we put that together with our 5 and we get the number 5.375. So this number, 101.011 in binary, means 5.375 in decimal. So that direction is the easier direction. The slightly more complex direction is going backwards, converting, for example, 5.375 to decimal. So convert 5.375 to binary. And again, we do this in two pieces. First, we convert the 5 to binary. And we may know 5 is 101, but if we don't, we use our algorithm. 5 divided by 2 is 2 with a remainder of 1. 2 divided by 2 is 1 with a remainder of 0. 1 divided by 2 is 0 with a remainder of 1. And then forevermore, 0 divided by 2 is 0, remainder 0. These remainders give us our number. So the number 5 corresponds to 101. And then step 2, we need to convert the decimal point 0.375 to binary. And here our trick is to multiply instead of divide. So 0.375 times 2 equals 0.75. And we're going to ignore the left of the decimal point. We're just going to take the decimal part. 0.75 times 2 equals 1.5. Ignore the left of the decimal point, just take the 0.5. 0.5 times 2 equals 1.0. Ignore the left of the decimal point, just take what's on the right. 0.0 times 2 equals 0.0. And again, this would continue forever. And now we look at these remainders. So we have these remainders of 0, 1, 1, 0, 0. And this time, these go to the right. So we get 0, 1, 1, 0, 0. And if we continue multiplying 0 by 2, we'll keep adding zeros to the right. So this number 3.75 corresponds to 0.011. And then we could add, zeros to the end forever. So by this algorithm, 5.375 converts to 101.011, which was what we started with, 101.011. So we can double check our work like that. So we can go back and forth between binary and decimal for things that are not just integers. And again, the way to think of it is just the things to the right of the decimal point are the negative powers of 2. Just like in regular decimal, we learned that this is negative powers of 10. This is 0.1, 0.01, 0.001, and so on. All right, so with that, we can do our conversions back and forth. So next time we want to extend this representation idea to let us deal with negative numbers. And then we want to go ahead and start digging deeper into truth tables and start looking at how we connect truth tables and logic operations with things that we actually care about, like building circuits to perform particular functions. All right, thanks.